Avogadro's principle. It's quite useful. It says that when measured at the same temperature and pressure, so there's a requirement that pressure and temperature doesn't change, equal volumes of gases contain equal numbers of particles. Another way of saying this is, as the number of particles, I'm going to call that N, gets bigger, the volume will also get bigger. And we all know this from common sense. You have a balloon, it starts out pretty small, and then you put more particles of gas in there by blowing into it, and the volume of the balloon grows. To do this, do calculations involving this, because there are so many molecules, atoms or particles, molecules, that make up a sample of gas, it's useful to have a unit that encompasses a lot of these particles. And that unit is called the mole. The mole is it's a counting unit. It actually comes from chemistry. There's a definition for it that we don't have to concern ourselves with. But a mole is equal to 6.022 approximately times 10 to the 23rd particles. That's what a mole is. If you've had chemistry, you know about that number. Here's how we can practically use this. If you look at the periodic table that the chemists use, you find every element has got its own little square. And that square has got a number in there. There's a whole number. That's called the atomic number. Chemists care about that. We don't. This number is called the atomic weight. That's the weight in atomic mass units of the average atom of helium. In this example, He is helium. But more useful in most cases is the fact that this number is also the weight in grams of, or the mass in grams, of 1 mole of helium atoms. And that's called the molar mass. And it's got units of grams per mole. That's how many grams per 1 mole. And that can be used to find how many moles are present, how many particles are present in a certain weight or mass of gas. Let's take a look at this example problem. The question is, how many moles of helium are present in a 5.061 gram sample of helium? Well, let's get the little square from the periodic table up. And you can look this up for any element on the periodic table. Well, here's how we can solve this problem. We can use a dimensional analysis looking technique here. 5.061 grams. And I know that I want to have moles. That's the question. So I can use molar mass, because remember, this number is really grams per mole. So I'll put down here 4.00260 grams, and up here I'll put moles, and the grams will drop out, and that'll give me a quantity of moles. And if I do my arithmetic, this comes out to 1.264 moles. If you have a compound, like water, for example, or some other compound that's made up of more than one element, it's pretty easy to do this. You just add up the molar masses of all the elements that are in the compound. So for water, for example, you have 2 hydrogens and you have 1 oxygen. So to find the molar mass of water, I would take 2 times the molar mass of hydrogen, which turns out to be 1.008 grams per mole, and I would add 1 times the molar mass of oxygen, which turns out to be 15.999 grams per mole, and that adds up to 18.015 grams per mole, and then we can use that to convert from grams to moles, just like we did for elements. Related to Avogadro's principle is this idea of what's called molar volume. In other words, what volume does a mole take up? And to think about this in a kind of a standard way, we have something that's called standard temperature and pressure. Standard temperature and pressure is abbreviated STP, standard temperature and pressure. And the standard temperature is 273 kelvins, which is 0 Celsius. And the standard pressure is 1 atmosphere. When those conditions are met, when the temperature is 273 kelvins and the pressure is 1 atmosphere, this is true for any gas. 1 mole takes up 22.4 liters of space. So if we were to solve this problem, the question is asking how many moles of oxygen are contained in a bottle that has a volume of 2.35 liters at STP. Well, here's what you could do. Starting out as 2.35 liters, knowing that we're at STP, we have 22.4 liters for every 1 mole. So liters will drop out, and this will tell us how many moles are in there. Do the arithmetic, you get 0.105 moles. There's another problem that asks us to work the question the other way. What's the volume? You're trying to find volume. It's at STP, so we know that every mole is going to take up 22.4 liters. So we start out with 10.5 moles. Now we multiply by 22.4 liters per mole. And this is going to give us volume in liters. And that number, if you do the arithmetic, is 235 liters. Well, what would be really nice is to be able to get rid of that last restriction, that the number of moles of gas can't change, that fixed quantity of gas restriction, and have a relationship that puts all the 4 variables, pressure, volume, moles, and temperature together. Moles in gas law terms are abbreviated small n. Capital N is particles, but small n is moles. Well, here's what we know already. We know from Boyle's law that volume is equal to, or it's proportional to, 1 over pressure, the inverse of pressure. We know that volume is also directly proportional to temperature from Charles' law. And we know that volume is directly proportional to number of moles from Avogadro's principle. So if we take all these things together and sort of smush them together into one law, we know that volume is proportional to temperature, it's proportional to number of moles, and to the inverse of pressure. So volume is proportional to the product of temperature times number of moles divided by pressure. If we turn that into an equation by just introducing a constant, the slope of a line, we get volume is equal to K times T times N divided by P. Well, that constant of proportionality turns out to be a really important number in science. And K is called R. This is the universal gas constant, R. And the equation is usually written this way. P times V equals N times R times T. A very famous equation in the physical sciences called the ideal gas law. It says that the product of pressure and volume is equal to the product of number of moles times this constant times T. A good thing to do would be figure out what the value of R is. Starting out from the ideal gas law, PV equals nRT, let's solve for R. We could do that by dividing both sides by N times T. So R is PV over N times T. Let's plug in some numbers for conditions that we know, and that's standard temperature and pressure. The standard pressure is 1.0 atmospheres. The standard volume, well, that's 22.4 liters if number of moles is 1 mole. And the temperature would be standard temperature, and that's 273 kelvins. So if you do some unit analysis here, you're going to get liters times atmospheres on the top. You're going to get moles times kelvins on the bottom. And if you do your arithmetic, this is what you get, 0.0821. That number, the universal gas constant, it's amazing how many places that shows up in science. It's pretty astonishing. Let's solve this problem using the ideal gas law. Here's the information that's given to us. There's a volume. The pressure is given, set at 685 torr. There's a temperature. And the question is, N. How many moles are in the bulb? Well, let's set this problem up using the ideal gas law. Pressure times volume is number of moles times R times T. N is what we're trying to find here. So that would be PV divided by R times T. Now, because of the units on R being liter atmospheres per mole Kelvin, anytime we put a volume in the ideal gas law, that's got to be in liters. Anytime we put a pressure in, it's got to be in atmospheres. And anytime we put a temperature in, it's got to be in kelvins. So let's do some conversions here. We know from the problem that our pressure is 685 torrs. but we want that in atmospheres. So we'll use the conversion that we learned earlier. 760 torrs is the same thing as 1 atmosphere. So this will give us atmospheres, and it's 0.901. Our volume is 300 milliliters, but that's got to be in liters. With 1,000 milliliters per liter, that's going to give us 0.3 liters. And our temperature has got to be in kelvins, and it's not. It's 26 degrees C. So if we add 273 to that, we're going to get 299 kelvins. So plugging that stuff into the ideal gas law, we find that N is equal to 0.901 atmospheres times 0.300 liters divided by R, 0.0821 liter atmospheres per mole Kelvin, times our temperature, which is 299 kelvins. And kelvins are going to drop out here. Liters are going to cancel. Atmospheres are too. And the only thing that you're going to have left is 1 over the reciprocal of moles, which is just moles. Do your arithmetic. 0.0110 is the answer.